Hello everyone. In this video lecture, we'll learn about design of a fermenter. So this cartoon figure it shows different parts of a standard fermenter. Okay, so usually a standard fermenter it should have some parts. I mean to for fulfill its various functions, such as okay. So first, let's talk about the shape. Usually, I mean the fermenters they're usually cylinder shape. Okay, like a big cylinder tank. Okay, which are vertically erected, and I mean in not in all, but in most of the fermenters, there should be a stirrer like this. Okay, which is which is rotated mechanically, and the stirrer is contain some impeller. Okay, there can be a single impeller or there can be multiple impellers. Okay, and the role of impellers is to mix. Okay, for mixing, and there should be inlet for to inject air, sterile air into the fermenter and to asperge the gas. Okay, we use asperger to asperge the gas inside the fermenter, and it should also contain input point for steam. Okay, and and also it I mean a fermenter it has several other parts or equipments. Okay, to control many different parameters, the parameters which are essential to process, I mean to run the process efficiently, like it should have pH controller, temperature controller. For controlling the temperature, usually I mean water is used. Okay, so I mean usually the fermenter they are wrapped by a cooling jacket. Okay, and this I mean the fermenters they have several sensor in it, like pH sensor, temperature sensor, pressure sensor. Okay, and based on the data of the sensors, the equipments like the pH controller they adjust the pH, temperature controller they control the pH. Okay, and also the fermenters they have several other points, for example points to harvest samples. Okay, and points to uh, add something like I mean if you do the fermenter in a continuous way, in that case you have to add I mean continuously add media on it. Okay, fresh media on it, so the fermenter should also have that kind of points. Okay, so anyway, so when you need to design a fermenter, you have to consider several points such as sterilization. I mean, how we are going to sterile the our fermenter. Okay, so before running, the fermenter need to be prepared, and that steps we clean the fermenter, we sterile it. Right, we cannot do a fermentation in an unsterile container. Okay, and temperature control, power consumption. This is important. The less the fermenter consume power is more better. Okay, because if it consume less power the cost will be lower, and it's always good for the industry. There should be pH control, foam control, evaporation loss, aeration and agitation, sampling point. I mean, from the fermenter, time to time, we have to collect the sample for testing. Okay, and inoculation points for microorganisms, media, and supplements. It's important. I mean, if you do run your fermenter in a batch system, in that case these are not necessary, because in the batch fermentation process we put everything inside the fermenter and just run it. Okay, and we don't add anything, we don't remove anything until the fermentation is done. But in case of continuous fermentation, as I just said, we have to continue. I mean, we have to continuously add fresh media, microorganisms, supplements. Okay, so that's why there should be, I mean, input point there to add these things. Okay. Then drainage point for drainage of fermented media, harvesting of product, cleaning, facility of providing hot and cold water and sterile compressed air, minimal labor requirements, use of cheapest materials which enable satisfactory results, similar geometry. Okay, these 2 points, like minimal labor requirements and use of cheapest material, which enable satisfactory results. These points are actually important because if your fermentation process require lots of labor, I mean many labor, that means the cost will increase. Okay, and which will not be good for the industry. And also, if you can use cheapest material, okay, such as raw materials, cheaper raw materials, the cost will be also again lower. Okay, and similar geometry. Okay, so what you understand by similar geometry means, like, we just don't go directly to the final big fermenter, right? Before that, we scale up our process. I mean, first we develop the process in the lab, then we scale it up. Okay, we just don't directly go to the bigger one. So here, by similarity in geometry means the design, the geometry of the final fermenter should be same as like the design of the pilot fermenter. Actually, in pilot fermenter, we do the scaling up. Okay, so if the geometry is same, then there will be less variation. I mean, the geometry same means the environment inside the fermenter will be similar. Okay, so that means when we transfer the, I mean, our culture organisms from the pilot fermenter to the main fermenter. If the geometry is similar, the environment will be similar. So that's this. I mean, the cultures from the pilot fermenter will not feel any variations there. Okay, so that means they will require less time to adapt. It will speed up the speed up the fermentation process, definitely. Okay, we don't have to lose any time. I mean, we don't have to give the biocatalyst any time to get adapted with the new environment. Okay, that's why it's important that the geometry of the final big fermenter and the pilot fermenters will be similar. Okay, so these were the points that we should keep in our mind when we want to design a fermenter. Now, let's talk about the parts of the fermenter. You actually already know. I mean, when I was talking about this figure, I already mentioned several parts. I mean, mentioned about several parts. So, just for recap, okay. So, the major parts of fermenter. Major parts means these are not all the parts that a fermenter has. But these are, I mean, usually all the fermenters, they they contain these parts. Okay, these major parts. So such as material. I mean, in which material the fermenter is built. Impellers, baffles, inoculation port, asperger, sampling point, pH control device, temperature control system, foam control device, bottom drainage system. These are the basic or major parts that a standard fermenter have. Okay, so now in the next slides, I'll talk in details about these different parts. First, start with the material. So which material we will use to build the fermenter. Okay, so the material used for designing a fermenter should have some important functions or important properties. Those are: it should not be corrosive. Okay, it should not add any toxic substance to the fermentation media. It should tolerate steam sterilization process. It should be able to tolerate high pressure and resist pH changes. This third point, I mean, it should tolerate steam sterilization process. This is very important because I mean, we have to sterilize our fermenter before starting a new process. Okay, and I mean, there are several methods for sterilizing. Like, for example, uh, which one is the most common sterilization process that we use in our laboratory? Autoclaving, right? But I mean, we can autoclave smaller things. The fermenter itself is very big, so we cannot just sterilize by autoclaving. Okay, so for the industry, stream sterilization is the most frequently used and the famous process. Okay, so that's why it's essential that the material that we will use to build our fermenter will withstand the heat of the steam. Okay. Okay. Some more information about the materials. Okay. So the fermenter material used is also decided on type of fermentation process. I mean, what type of fermentation we want to do. For example, in case of beer, wine, lactic acid fermentation, the fermenter tanks are made up of wooden material. However, metals like iron, copper, glass, stainless steel can also be used in some cases. Okay, so let me clarify it. So, usually in the traditional fermenting process, like you heard about the word brewing industry, there are some traditional brewing industry and there are some commercial brewing industry. There are many traditional brewing industry all around the world, and in the traditional brewing industry, they usually use wood to build the fermenter. And in those traditional, traditional brewing industry, basically the fermenter is smaller, okay, not very big, and there is reason why they use wood. You know, so when you ferment wine or that alcoholic beverages, if you do it in the wood itself adds some extra characteristic to the alcohol, especially flavor, tastes. Okay, and these are important in the traditional brewing industry because every traditional brewing industry they have usually have some unique taste. Okay, some uniqueness. Okay, so that's why they just don't use any wood. Every brewing industry they use wood from some particular trees. Even actually once I visited one brewing industry in USA, they used to use wood from some specific trees which are raised in, which are grown in Greece. Okay, and that traditional industry always use wood from that trees which are grown in Greece, not even in USA. Okay, so they always used to try to use the same wood. Okay, so that's why they can, produce their alcohol with a consistent taste. Okay, however, like traditional brewing is costly. So the industry, who produce alcohol, like alcoholic beverages in mass amount, okay, they usually use, they don't use wood as fermenter material. Okay, they prefer to use stainless steel. Okay. Okay, and finally, a fermenter should provide the facility to control and monitor various parameters for a successful fermentation process. Here, parameters mean pH, temperature, pressure, foam. Okay, this. So, we learned about the basics of fermenters. Now, we will learn about some fermenters. Okay, some different types of fermenters. So based on the design, all the bioreactor fall into three fundamental classes. Fermenters are also called bioreactors, fermenters, same thing. Okay, so all the bioreactor design fall into three fundamental classes. One is called stir tank bioreactors, bubble column bioreactors, and airlift bioreactors. Okay, so first I'll talk about the uh, steel tank bioreactors, STR. Okay, in this kind of bioreactors, mechanical impeller are used. Okay, mechanical stirrer are used for mixing. Okay, and these are the most common type of fermenters which are widely used around the world. Okay, however, sometimes like if the media that we used for the fermentation is if the concentration is high. Okay, in that case there is a chance that the soluble oxygen will rapidly deplete. And if the soluble oxygen is depleted, it can create an anaerobic condition. Okay, and which will hamper the process. Okay, however, these difficulties, this problem can be resolved actually. To resolve that one, people put a air inlet here, okay, to inject oxygen continuously here, okay, by using asperger, this one, by using this device. Okay, there is an air inlet and asperger to continuously inject required amount of oxygen, okay, which can prevent the anaerobic condition formation. Okay, state and bioreaction. Some more information about state and bioreactors. These are good to know. Uh, the state tank bioreactor, they require high input of energy because we have to mechanically stir. Okay, So we have to use the motor, mechanical stirrer. They will definitely require some energy. Okay, and as we steer it mechanically, vortex is a problem here. I mean, it shakes, it can shake vigorously, which will be, I mean, not a safe thing, right? Suppose you have a very big fermenter in your industry and it's vigorously or dangerously shaking, okay, that will be dangerous. So, I mean, this problem can be resolved by using baffles. Okay, so baffles are used to reduce vortexing. Okay, and uh, regarding the size and shapes of the impeller, there are many different types of, I mean, different impeller of different sizes and shapes. Okay, so which one we will use? I mean, which design of impeller we will use completely depend on the type of the process. I mean, which type of cell you are using for your fermentation. Okay, and some fermenter they may have only one impeller. Some fermenter or bioreactor they can have multiple impellers. Okay, and multiple impellers they improves mixing. Okay, and in this type of fermenter we don't fill it up completely, right? Usually only 70 to 80% of the volume of stir tank reactors is filled with the liquid. That means we have to keep some empty spaces here. Okay, this is important actually. Why? One is for gas disengagement. Okay, for the gas disengagement. Also, foams. I mean, when you run the process, foams are continuously formed, so there should be a space for that foam here. Okay. Okay, and however, I mean, foam is a problem. Okay, if there is foam in above the, I mean, here in the fermenter, in top of the fermenter, this foam prevent or hampers the gas disengagement process. Okay, so that's why in the fermenters, people always use foam breaker. Okay, and foam breaker can be different. You can use like some mechanical device to manage the foam, and also people use chemical anti-foam chemicals, okay, to reduce the or remove the foams. Then aspect ratio. Okay, aspect ratio means the ratio between the height and width. Okay, height and width. Okay, so the aspect ratio is important for the proper uh, what you can say mass transfer. Okay, for the proper mass transfer. Okay, so I mean, usually, I mean, what aspect ratio we need to use, again it depends on the type of process that we will do in that fermenter. Okay. Okay, and okay, one thing that I need to tell about this bioreactor, that as we are I mean, mechanical impellers are used in this fermenter. Mechanical impellers they creates high shear force. Okay, shear force can harm the cells that we use in the fermenter. Okay, so that's why we should be careful. Okay, we should be careful about the catalyst or cells that we use in the fermenter. Okay, so basically, when people do the scaling up, okay, they optimize the parameters. I mean, in what type of impellers, I mean, what design of impellers should be used, and what should be the speed of the impellers, okay, which will be like less harmful for the catalyst but will help to produce maximum yield. Okay, so our goal is always to hamper the cell as less as possible and maximize the production. Okay, so this was about the stirred tank bioreactor. Then bubble column bioreactor. Okay, in this type of bioreactor, mechanical stirrer are not used. Rather, bubbles, that means gas, air, or other gas are used to achieve the required agitation. That means mixing. Okay, and bubble column reactors they require less energy than the mechanical stirrer, and bubble columns are applied industrially for production of baker's yeast, beer, and vinegar, and for treatment of wastewater, etc. Okay, and in case of bubble column bioreactors, uh, the aspect ratio is usually 3:1. Okay, for Baker's yeast production. For other applications, aspect ratio of 6 is to 1 are usually used. I mean, usually they use 6 is to 1, but for Baker's yeast, it should be 3 is to 1. Okay, and some advantage of bubble column bioreactors are low capital cost, lack of moving parts. Lack of moving parts means maintenance is easier, and satisfactory heat and mass transfer performance. Okay, yet I mean, although we don't use the mechanical agitator or I mean stirrer here, foam still can be formed. Okay, and it can create problems. Okay, anyway, I mean, in the bubble column bioreactor, what we use for the mixing? Air. Okay, so based on the speed that you are, I mean, injecting your air, two different type of flow can be achieved. Okay, so basically what type of, I mean, those two are homogeneous flow or heterogeneous flow. So which kind of flow will be produced depend on which pressure or in which velocity you are injecting the air. So in case of homogeneous flow, all bubbles rise with the same upward velocity. Basically, actually, this photo, it represents the homogeneous flow. I mean, all the bubbles, they go up in the same velocity. Okay, and there is no back mixing of the gas occurs here. In the contrary, in case of heterogeneous flow, a higher gas velocity, bubbles and liquid tend to rise in the center of the column, while a corresponding downflow of liquid occurs near the walls. I mean, as we inject the air in high velocity, that means with high pressure, so at the center, at the middle, the bubbles, they go upward in high velocity or force. Okay, so this high upward velocity or force, it creates a downflow near the wall of the bioreactor. Basically, they move like this way, this and then this. Okay, it creates a back mixing. Okay, then the third type of bioreactors, airlift bioreactors. Okay, these are almost like the bubble column bioreactors, but there are some differences, basic differences. Okay, in the design. So, and because of the differences in the design, the flow or mixing achieved in airlift bioreactors are different. Okay, and I mean, if you look at this figure, basic, I think, I mean, it will be easier to understand. So look at this one. So air is air inlet, that means air is injected from here, so go upward, and then they go down here, again they go upward. Okay, it creates a mixing. Actually, can you see this line? This lines means there is another structure inside the this fermenter. Okay, in the bubble column there is no such structure. Okay, but in case of airlift bioreactors, there should be some structure which will facilitate this kind of movements. Okay, this kind of movements. And the airlift bioreactors, they can be of, I mean, the design can be different. I mean, usually they have two types of design. One is this type. Okay, so another, I mean, this is the original bioreactor, and inside the bioreactor there is some columns. Usually these columns are made of, also made of stainless steel. Okay, but this, I mean, this facilitates the mixing. So in case, I mean, there are two types: internal loop, external loop. Actually, it creates a loop. Okay, but you can design it in a way that the loop will be inside the fermenter, or you can design in a way that the loop will be outside, like this one. So, like in this case, the mixing is in this way within the fermenter, but in this case, the mixing is like this way externally. Okay, it creates a external loop. Okay, so external loop have some benefits over, or I mean, the external loop have some advantages over the internal loop. I'll talk about it in a later slide. Okay, first let's have a look in this slide. I mean, the external loop types of reactors, we can design in different ways, like two-stage air-lip bioreactor. Okay, it has two external loop. Okay, okay. Let's try to learn more about the airlift bioreactors. Airlift reactors are often chosen for culture of plant and animal cells, and immobilized catalyst because shear level are low. I mean, the animal and plant cell, they cannot withstand high shear force, which is created in the stirred tank bioreactor. So that's the stirred tank bioreactors are not a good choice to culture. I mean, to do fermentation with plant and animal cells. Okay, so as in the airlift bioreactors, there is no mechanical. There is no mechanical stirrer here. So that means the shear force generated or created inside the airlift bioreactors is low. Okay, so that's why this type of bioreactors, they are good for. Is good for the plant and animal cells. Okay. Okay, and I already told you that uh, internal loop vessels and external. The early bioreactors, the design can be of two types: internal loop vessels, external loop vessels. Okay, and I also I told earlier that the external loop bioreactors, they have some advantages over the internal loop bioreactors. So what are those? Okay, so because of the riser and downcomer are further part in external loop vessels, gas disengagement is more effective than in internal loop devices. So the gas disengagement is better in case of internal loop devices. So what we understand about the gas disengagement? Okay, I'll try to explain you. So, say in this bioreactor, so we are injecting air. So, what will happen? The air will form bubbles and go upwards. So, why we are injecting the air? Just to achieve the mixing? Definitely no, right? We are injecting the air. Yeah, achieving the mixing is one of our goal, and another goal is the the materials inside the bioreactor, the cells, they require oxygen, right? So from where they get this oxygen? From the air that we are injecting. So after we inject the gas or the air, they form bubbles. That means inside the bubbles there is the oxygen. So this oxygen need to be transferred from the bubble to the liquid medium. Why the liquid media contain the cells? Okay, so this is called gas disengagement. Okay, the oxygen is transferred from the bubbles to the cells by gas disengagement. Okay, another gas disengagement also occur in the top. I mean, from the bubbles, the oxygen is transferred to the cells. In the when the fermentation process run, toxic or bad gases are also produced, like the carbon dioxide gas. Okay, so those carbon dioxide gas should be removed. Okay, this also happens in the through the disengagement process. Okay, in the top. Anyway, let's go back to the gas disengagement of oxygen. So oxygen need to be transferred from the bubble to the gas. So that means for doing that, the bubble should be inside the liquid, right? So as longer the bubble will be inside the liquid, more oxygen would be transferred, right? So like think about this one. Okay, the bubble column one. We are injecting the oxygen, air, that means oxygen. Okay, so bubbles are formed here. They go upwards. So by this time, the gas engagement should be done within this time. Okay, but in case of the airlift reactors, the bubbles, they recirculate within the media. So that means the bubbles get more time to transfer the oxygen. Okay, this is true for both design, the internal loop or the external loop. But in case of external loop, okay, the bubbles get, the recirculation is better than the internal loop bioreactors. So as the recirculation is better in case of external loop, the bubbles get more time in the recirculation. Okay, that means they more time to transfer the oxygen. That means gas disengagement is better in case of external loop bioreactor. Okay, so this was one benefit. There is actually also other benefit. Okay, so like I mean, not only the gas disengagement, uh, the mixing is better in case of external loop. The mixing is an important thing for bioreactors. Like so, in the bioreactors, we put cell, the media, that means the food for the cell, and also various other chemicals, like we can put supplements, like the vitamins, like the other required essential proteins, etc., etc. Okay. So if the mixing is not good, I mean, so say for example, the cells are in the media. So what they need? They need nutritions. Okay, so and where the nutritions are? The nutritions are in the liquid media. Okay, so if the mixing is better, the cells will easily get the nutrients, right? So if the mixing is not good, what will happen? In one part of the bioreactor, there will be less nutrients, less oxygen. In another part, there will be uh, more oxygen or more nutrients, and this will be a problem, right? I mean, there will be no even distribution of the nutrients, so growth of the cells will be hampered, and if the growth of the cells is hampered, the production will be hampered. Okay, so better mixing means better yield. Okay, better mixing means better growth of the cells, that means better production. So, and we can achieve better mixing in case of external loop bioreactors than the internal loop bioreactors. Okay. Okay. However, anyway, so we are done with the three types of bioreactors. Okay, among these three types, traditionally and industrially or commonly, STR, the ST type bioreactors are most famous. I mean, they are most commonly or traditionally used. Okay, why? Because this type of bioreactor has several advantages over other bioreactor configurations. That means other type of the bioreactors. What are those advantages? It has highly flexible operating conditions. Okay, very flexible operating conditions. Okay, you can change the operating conditions. For example, you can change the speed of the rotator. Okay, that means you can change the speed of the impeller and of the steerer. You can change the I mean, pressure or velocity of the incoming air. Okay, so you can control this. I mean, very flexibly with I mean we with high flexibility we can operate the process. It is readily available commercially. Okay, and it provides efficient gas transfer to the growing microbial cells. Mixing is best in stirred tank bioreactors. I mean, there is a problem. Stirred tank bioreactors create shear forces, but mixing is best. If and as the mixing is best, the gas disengagement, that I mean, in simple word, we can say the gas transfer is better. That means efficient. Okay, in case of STR, stirred tank bioreactors. And finally, it has been used extensively by fermentation engineers and microbiologists for growing a variety of microorganisms. So as it is extensively used, people have better idea about this kind of fermenters. Okay, I mean, that means we have better knowledge about this kind of fermenters. Okay, so these were some advantages of stick tank bioreactors over other other type of bioreactors. Okay. So that's all for this video lecture. In the next lecture, we'll learn about, I mean, there are, I mean, these three are the major types of bioreactors. That doesn't mean that these three are the only one. Actually, there are some other types of bioreactors, and in the next video, we'll learn about those. Till then, be safe. Thank you.